Great. And a reminder, the chat log gets recorded as well. I think everyone knows that at this point. Great. Okay, week 4, and this is the 7th class, and we're looking at linear regression. So just to recap from last week, and again, let me give the high-level overview. As always, we'll be going through some topics related to linear regression, and then we'll have time at the end to do some admin stuff. We'll talk about the questions on the coursework and planning and so on. Great. Okay, I'll turn off my webcam just to save bandwidth. Okay, so what did we do last week? Last week we did generalization. So we looked at concepts like our training error or training loss. What we cared about really was some kind of notion of generalization. And we saw how we could kind of empirically estimate that in some sense with our test loss, test error. We did see some questions around that. In some sense, a test set is this very special set of data that we shouldn't be looking at too much when we train. And so we talked about questions around how do we actually measure performance without overfitting to our test set. And so those included questions like questions around validation sets, for example. So we could use that for choosing hyperparameters. And what do I mean by hyperparameters? We looked at things like, in some sense, controlling for complexity of our models. So, for example, in decision trees, we have this maximum depth parameters or the minimum number of examples at leaf node, and so we can tune these parameters on our validation sets. Okay, so evaluation, again, another kind of key or critical part of machine learning. We looked at evaluation from the context of classification. Okay, so we looked at metrics like accuracy. We also looked at how we can reason about our performance in terms of ROC curves, okay? So true positive rates and so on. But then we also looked at this from the concept of regression. And we saw things like mean squared error and so on. Up until now, we've really actually in the course, we've only focused on the actual classifiers. And so today we're going to be looking at regression. I guess we did do a bit of regression for the decision trees, but today we're going to look in more detail. Okay, so like I said, linear regression for today. Great, so I'm going to go through this stuff reasonably slowly, just so that we're all on the same page. Okay, so what are we trying to do? So in the context of regression, we have our training set. Okay, so we're going to have some attribute vector x. We're going to have some target or scalar value y. Okay, and we have a training set of these. So we have I equals 1 to n. So what do we have? We have n of these examples. Okay, and just to really make it verbose, we can just illustrate what we mean by each of these terms again. But this is all kind of recapping. We're familiar with this from the context of classification. So we have some d-dimensional attribute vector. Okay, in a sense, the inputs to our algorithm. And we're going to have our the quantity that we're trying to actually regress. So you could call it the target, for example. Okay, so this is a continuous real value. In the context of classification, we thought of this in terms of discrete labels like -1 or 1 or 0, 1 or 0, 1, 2, 3, 4, etc. Okay, and so let's look at a simple 1D example. Okay, so let's say, for example, I have measurement rainfall. I keep doing rain examples, so apologize. I'll have to do sunshine examples. And let's say it's umbrellas sold. Okay, and we're modeling the relationship between those two things. So in a sense, our rainfall is going to be our attributes, and our umbrella sold is our y value, our continuous target of the output. Okay, and so for example, let's say we can make some measurement. We go to a particular city and we can make a measurement, and we read off some value of rainfall and the corresponding umbrella sold. And then we can do the same for a different place, and so on. And obviously, there's a corresponding rainfall and umbrella sold for each of these examples, and so on. And you can imagine we could amass a data set like that. So today we're talking about linear fitting, so fitting linear models to this type of data. And so we could think of that, I guess I'll draw a straight line. We could think of that in terms of this fitting in this one-dimensional example are fitting this line to our data. Okay, so that's our linear model basically. And so what are we saying? We're making a pretty big assumption. Okay, we're making an assumption with our model. So this is going to be our model. It's going to be some model with respect to this semicolon, sorry, with W. And we're saying basically that there's this linear relationship between our attributes and our weight vector. So these are going to be the parameters of the model that we learn. And this is our continuous output value. And again, so to be clear, this is our weight vector. And today we're going to talk about how we actually estimate this. Okay, and remember, let's like an aside, we should always remember, we're always talking about column vectors unless specified otherwise. Okay. And sorry, yeah, that's a bit unclear. That's not an Xij. That's supposed to be a semicolon. Just indicating that it's some function of the weights. Okay, and so this would, what would this be here? This would be a 1 by d, and this would be d by 1, and so we'd have a single scalar value. Yeah, we'll get to that, whether it should be d by d plus 1. You're right. I guess I'm kind of glossing over some of these details just to keep the discussion a bit more high level. We'll get to that. Okay, and so we can look at basically the discrepancy between the actual values that we measure, target values that we measure, and our model predictions. Okay, and so we can call that residual. So what does it mean? For each item in our training set, we can look at the discrepancy between what our model predicts. So again, these are our estimated parameters, and this is the value that we would that we're aiming to reach. And what we'd like, obviously, is for these residuals to be small. And so in a sense, you can think of these residuals as measuring the discrepancy between the fit of our line and the actual real data that we have. So we can define, and so this is kind of intuitive. Now we want this value to be small. And so we can define a loss function. Okay, so we're going to have some loss with respect to our weights. And we could just think of this as a sum over all our training examples. Okay, but there's one thing that's quite important here, is that we want to take a square of this. And why do we want to square it? Because we're going to have some negative discrepancies and positive discrepancies or residuals. And so obviously we don't want them to cancel each other out, so we can square those terms. And so what do we have here then? We have the sum, so i.e. sum of the squared residuals. Okay, yeah, so don't get too hung up on the notation of this. It's just to indicate that it's some function of the input and the weights. Okay, and so what we've seen also elsewhere is we can see this specified or called kind of our error or loss. So this is the same quantity here, loss. Okay. Yeah, and so for example, again, I've just done a one-dimensional example on the other slide, but for example, this could be our target value y, and this could be some attribute x1 and some attribute x2 that we can measure. And so again, we have this linear fit, or this kind of hyperplane that we're fitting to our data, and we can see that the lines associated with each of these indicating the kind of residuals or how well this fits our data. Okay, so there's a lot of, there's some talk about the nature of the loss and whether we need 1 over n. So again, imagine if we're minimizing this loss, and we'll get to this later, those kind of constants won't actually make a difference. And then the order of the transpose, so remember, this thing is just ultimately going to be a scalar. Exactly, dot products written in different ways. Great, okay, so we've, let's take a kind of a slight detour. And we'll look at one way to represent this in terms of vector notation. Okay, So what are we trying to represent? So we're going to have our vector of y values. I'm going to use a design matrix X, and let me define that now. And this is going to be our vector of residuals, okay? So I'm going to do a slight abuse of the notation from the lectures just for convenience, just to keep things, just to make it easier for me to write during the slides. But we've seen our design matrix in terms of the lectures defined as our kind of phi. But what does it contain? Basically, it contains our attribute vectors transposed, so turned into row vectors. And so we'd have all n of these. Okay. And someone rightly pointed out earlier on, what we've seen in the slides is that we append a 1 onto this so we can take into account the bias term. So in a sense, this is our n by d, technically plus 1, but let's just pretend for now, or we can assume for now that our d already includes that plus 1. It's not actually important really for our discussion today, and I don't want to overcomplicate things by adding all this extra. Yeah, so the 1s are the y-intercept, so you've seen that already in the lectures. Okay, so let's look, let's just remind ourselves what's going on here. So there's a column vector, some n by 1 column vector. This is some n by d design matrix. This is our d by 1. And so we can see what's going on here. We'll basically have our n by 1. So this is the residuals for each of the training examples, just written out in vector notation. So we can go back to our loss. Remember, this was our LFW that we defined, okay? And we can actually write this out in terms of vector notation as well. So again, this is going to be the inner product of these two vectors. So if I take the transpose of this, it's going to be a 1 by n times the n by 1. So this is going to be a single scalar value, which is what we expected from our loss. And if we write this out, this is our y. What have I done? I basically taken the equivalent, I've written in the equivalent of our squared residual. So we basically have a residual vector, transpose it, times another residual vector, which is the equivalent, obviously, of squaring each of these elements. And if we just jump back for a second, you can look at this yourself, but you should be able to convince yourself that it's actually just writing out the same thing in terms of vector notation. Great. Okay, so in a sense, this is our, we've just defined our last function now in terms of these residuals. Okay, so what is our objective really? So our goal is to solve for some weight vector W that minimizes our loss. Yeah, transpose so that we have this, this is at n by 1, remember, we up here, and this is 1 by n when we take the transpose into account. So we can effectively do the dot product between these two vectors. Okay, so our goal is to estimate this W value, and our plan, the way we're going to go about this, is we're going to take the derivative of this loss function with respect to the weight vector, and then we're going to set it to 0. And our aim, or our answer that we want to get to, we've seen in the slides, is an expression for W that's of the form. Okay, so we're gonna step through how we actually get from here to here. That's going to be our objective. Okay, so let's take another brief aside and talk about minimizing functions. So minimum. Okay, so let's say I had some quadratic function like this. Okay. So let's call this our x. Sorry. X, and this is just some function of x, g of x, for example. So what is our g of x in this example? Okay, so it's just some function that's a square of x minus some constant. And what we should know from, I guess, simple calculus that we've all done before, maybe not even at high school, we take the derivative of this with respect to x, okay? Take the derivative of our function with respect to x, and we're going to set it to 0 to be able to find our minimum, okay? So this is going to be 2x minus 2, and inside of this bracket, just a constant with respect to x. So this is equal to 2x minus 4. If we set this to 0, okay? So x is going to equal 2. And this makes sense. It makes sense here. If we had 2 here, this would be 0 squared, and this is going to be the minimum of our function. Okay, and so, this is calculus with simple kind of scalar quantities, something that we're quite used to. And what we're going to do today, and what you've seen in the lectures, is we're going to kind of make a slight generalization to this way of working to make matrix calculus, so we can do solve basically for our W values, the weight vectors for linear regression. And maybe let me make a quick pointer to something that we're going to see in future weeks. So in future weeks, actually next week, we're going to be looking at gradient descent. So that we're going to be looking at taking the gradients of functions with respect to the parameters we care about, and taking steps in the negative direction of the gradient towards some kind of, hopefully, towards a minimum. And so in the context of convex functions, we'll have some global minimum. Okay, so we should already be comfortable with taking derivatives of scalar quantities with respect to scalars. So like we just did there. So this is a scalar. This is a scalar quantity. But the leap we're going to have to make today is when we have, so let's see, is when we have vectors, okay? So we're going to have some function, like for example, our loss. And we're going to have to take the derivative of the partial derivatives with respect to the weight vector W. Okay. Remember, our loss is a scalar quantity, but this is actually a vector, the W. Okay. So let's take a look, a small digression into the kind of matrix calculus that we need. Okay, so really, I guess matrix calculus, it's not that it's necessarily a whole different branch of mathematics. It's just really shorthand for doing multiple calculus operations in one shot, in one step. And so it can certainly make things a lot cleaner, because you don't have to write out explicitly all of these scalar quantities. But remember, at the end of the day, these vectors are just effectively lists of numbers and so on. Okay, let me just check the chat. Okay, we won't go into that, Angus. We'll definitely touch on a lot of this more in the near future. So hold your questions about optimization for now, if you don't mind. Okay, so let's say, for example, we have some function of our weights, okay, and it'll be of the form some vector A and some vector W. Okay, and so what we want to do, we want the derivative of this function with respect to the weights. Okay, so what's that going to look like? So the key thing that you should remember is that this derivative that we're going to compute, it's going to be of the same dimensionality as W. Okay, so we can think of this also as a column vector. Okay, where effectively what we're doing is we're taking the derivative of the function with respect to each element of W. W2, and I could go all the way on to WD. So D of these. Great. Okay. And so if we wanted to actually go about doing this, what we should remember, so let me write it out again. Remember what we have in this case, we have basically just a dot product between two vectors. Okay, so that's going to equal the sum. So I'm just going to write the dot product out explicitly. So we've got j elements aj times wj. Okay, and for each entry, obviously we're going to take the derivative with respect to that entry. So again, I'm just thinking about what each of the individual entries would be in this vector. And so again, we can write this out explicitly if we wanted to really kind of reason about what's going on. So we want to take the derivative of our dot product with respect to just one entry, wi, and we can just expand out our dot product. So what would that be? It'd be a1 w1 plus a2 w2. So I'm just being very kind of slow, and I'm working through the sum of this thing here. Plus dot 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 dot, ai wi plus dot 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 plus and there's d of these, remember. Okay, great. So the thing then we can kind of see from this, hopefully, is that actually most of these things don't depend on wi. There will only be one entry here that will depend on wi. So all of these effectively are constant with respect to wi because they're different dimensions or different entries of our weight vector that we don't actually care about for this particular partial derivative. And so the answer here then is just going to be a wi. And you could extend that logic basically to evaluating each of these particular entries. And what you'll find is that you'll have obviously the value of the derivative will be the element, the corresponding element of a. And so basically the derivative of this function in that sense will just be a. And this is kind of makes a bit of intuitive sense if we thought of this from the context of our scalar derivatives. If we had some constant like 2 times x and the derivative of that, clearly we would just be 2. Okay, and then the other thing to note here, okay, another aside, we looked at the derivative with this particular dot product, but it's actually the same thing if we switch them. Because this, all we've done is transpose and switch this around, but actually the operations are the exact same. So this thing would be the same. So let me draw a box around this so we don't get confused. Okay, and so we're going to be leveraging these tricks to be able to solve in a closed form, to get to a closed form expression for the weights of our linear regressor. The lines, okay, so we should know this by now, but the lines below below a and w, that's just indicating that they're vectors, no? So column vectors. Remember we said this in our notation. In this particular example, I've just defined it that we're taking derivatives with respect to w, not a. So a, in some sense, you could argue, or you could think that that as being a constant associated with it, a constant with respect to w. Yeah, we could have written it the other way around. We might care about solving for a, actually, and it would be the same thing. We'd just be swapping the letters around. But we just set this up with w because it kind of it sets us up for thinking about how we're going to ultimately take the derivatives of our loss with respect to our weight vector. Yeah. Yeah, and still, yeah, okay. Anything else? Okay, we'll keep going on. Okay, so let's get back to our linear regression finally. Okay, so we have our loss function. We have defined this already. Remember, we broke out the residuals into the 2 vectors. Okay, and let's just be really slow about it just to make sure that we're comfortable. Or I guess I've done it already. So this is our n by 1 vector. This is going to be a vector. We're going to transpose it to 1 by n, and this is going to be an n by 1. So when we do the dot product of those 2 things, we're going to get a single scalar value. And again, I'm kind of it's coming up in the chat a bit. I'm kind of hiding under the rug that our x, we could swap this in for our phi design matrix. So you could think of this as having your bias term already added. But again, like I said, it doesn't really, it's not necessary for our explanation here, and it's just going to clutter up the notation. Okay, so what am I going to do next? I'm just going to expand this thing out. Okay, so I'm literally just going to multiply different terms here. So the first thing we're going to do is multiply this y times this y, but we have to remember that this is transposed, okay? Then we're going to do our y transpose times our xw, and we have to take into account the negative, so this is going to be y transpose xw. Okay, great. Now we're going to multiply these two terms. So again, just multiplying out everything here. And so I won't apply the transpose yet. Okay, and then we have the final term here. So this is going to be xw transpose times xw. Yeah. Great. Okay. So let's actually let's look into a few of these expressions just to see if we can simplify this any further. So our first term is going to be xw transpose w. And again, you know, we can be really, you can kind of do the sanity checks all the time to make sure the dimensionality and all this stuff works out for you. So this would be n by d times a d by 1. But remember taking the transpose of all of this. So this is going to give you a d by 1. Oh, actually, let's apply the transpose first, and then we'll check that everything works out, just to make it clear. Okay. So we're just going to use the fact that this thing transposed would be this. Oh, sorry, I've written a y there, and I should have written that should be a y. Thanks if anyone caught that. Okay, that was my confusion. Okay, so I've just applied the transpose. So we need to just apply the transpose and swap the order to make sure that everything works out. And so if we looked at this, so this is going to be a 1 by d times our d by n times our n by 1. Okay. And so it's going to leave us a 1 by 1. And this kind of makes sense from a sanity point of view because we know that this has got to be a single scalar value. And so we would hope that each of these individual terms, when added up, they would all be 1s. Okay, so what have we got? We've got our weight vector times x transpose times y. Okay, but if we think about this, actually, we can kind of reason about this as basically just being this 1 by d vector times and the inner product with another vector, which would be d by 1. Yeah, when we apply this here. So alarm bells should start ringing. This kind of actually looks a bit like what we saw before, no? So we had something of the form of a vector, and we took the inner product with another vector when we were taking our partial derivatives. So we can just call that S for now. Okay. Again, I've just basically done the matrix multiplication here, and it ends up as a vector. Okay. So let's see if we can do anything with this one. So again, we'll do the sanity check. And so you wouldn't have to be as slow when you're working through this yourself, but it's actually quite useful to just go through it. Times our n by d times our d by 1. Okay, so that kind of all checks out in terms of our scalar that we would want. And we can think of this again, we can reason about this as being in a similar kind of way. Basically, we've just got some vector times our w, okay? So again, and it's the same quantity that we've observed here. Okay, and so you can kind of, you know, if you wanted to, you could work out all the indexing and kind of satisfy yourself that this thing actually is the same. But basically what we've got, when we work through this, we can figure out that these two things are actually the same quantity. And so we can rewrite then these two things. So minus yt, so just this term up here, minus our wt. So this is just going to equal Great. And okay, so what have I done? I've just realized that these two things are actually the same quantity, and then effectively then there's just two of them. And this shouldn't be too surprising if we think of this as like multiplying, a minus b squared. It's basically going to have some a squared type term, a b squared type term, and 2 times something else. Okay, so why am I expanding all of this? I'm going to expand all of this out so we can kind of get to a place where we can actually get to the take the derivative of this, and so it's going to be easier if we kind of simplify out the form of it. And did I miss a transpose? Yeah. It's okay. So let's write our slightly revised loss out. Okay, so this was the two terms that we combined in the last slide. Last term is the same again. Okay, so like I said, what do we want to do? What we said at the start that we were going to do is we were going to take the derivative of this with respect to our weight vector. Derivative of our loss with respect to our weights. Okay, so let's break it down into the individual terms. You can kind of look at these, call them A, B, and C. Okay, so we're going to take the derivative with respect to this term, respect to our weight vector W, and that should be kind of pretty obvious here, that this does not depend on W. So in a sense, you could think of this as a constant, and so this thing is actually just going to be 0. Okay, let's move on to the next term. Okay, we're going to take the derivative of so this does depend on W, okay? And so let's just put a note over here. So remember what we discovered before. Okay, so we saw, we worked through this before. And so what we have here, basically, we can think about this as being in a similar form to this. Again, we've got our vector W. So this is going to be our 1 by d times our d times n times our n times 1. So we can combine, again, this thing here and reason about this in terms of a vector and just the scalar quantity 2 that we're multiplying it. So this is minus 2 times this vector and the inner product of that with our W. And so if we work that out, it's basically, think of this, again, now we've replaced our A with this vector minus 2 times x transpose y. And so this is going to be the derivative with respect to W. Okay. Great. Okay, so I'm not going to go through explicitly how we would do this final term, but let's just write it out. And so this is what, like I said, I'm not going to go through it right now. This is what we would actually end up with. And if we think about all of this actually kind of maybe intuitively makes a bit of sense. Like we have some kind of quadratic term, it seems like here in terms of W. So you could imagine basically we have, if we had our scalar quantity, we'd have some like value a to the power of 2. And so when we take the derivative of that, we'd have 2 times quantity times whatever was remaining. Great, okay, so let us plug all these pieces in together. So again, like I said, we've already taken the derivative of each of these terms. Okay, so all I'm doing is copying over what we had before. Remember, this was 0. Okay, and what we said at the very start, we were just going to take the derivative of this, set it to 0, okay, to find the minimum. So if we set this thing to 0, we're basically, and let me do it in 2 steps. I'm going to set it to 0, and I'm going to move this to the, sorry, I'm going to move this to the other side of the equal sign. So we're going to have 2 times x transpose x w equals, okay, and so this is just a constant. We don't care about that. Right, so simply what we need to do is get rid of this term, or certainly move it up to the other side. So we multiply it, pre-multiply it by the inverse of it. And it brings us to the original solution, or the closed form solution that we described at the start. And let's do the sanity check as always. So what would you expect this to be? We'd expect this to be some d by 1 vector. And if we work through it, so this should be d times n, okay, n times d. The inverse isn't going to affect this because it's just a square matrix, times our, sorry, d times n times our n times 1. Okay, and so we can see that all the kind of dimensions of this line up, and we'd end up with our d times 1 vector. Great. Okay, so what did we do there? Basically, we went through rather slowly the process of deriving the solution for the linear regression model in terms of our weight parameters w. And we did this for matrix calculus in terms of our design matrix x and our vector of target values y. And the closed form means that we can actually, there is an expression for this. So later on, we're going to see in future classes when we're doing when we're taking gradients with respect to some of our functions, there isn't a nice, clean, closed form way that we can actually evaluate this expression. And so we're going to have to do some form of optimization to get to our values. So we're going to have to actually do, as I alluded to earlier on, some form of gradient descent, for example. Okay, so what else? Anything else here? Great. Okay, so that's really, I guess we have maybe what, like 10 minutes. Okay, so I'll skip ahead to the more admin stuff. That's really the main thing I wanted to get through. But the main kind of takeaway there for you guys is that hopefully you can see how we can get to this solution, and then really the power of linear regression that we've observed in the lecture notes is that we can apply the same type of reasoning, same type of model, and we swap out our x design matrix for more complex nonlinear basis functions. So we saw the polynomial regression, for example, or the RBF kernel that's used, and that allows us then to fit more complex models to the data that have nonlinear relationships, but actually still leveraging the underlying basic math of the linear regression. Okay. Great. Okay, so let's skip ahead to some of the admin stuff. So on Thursday's class, we're going to talk about logistic regression. Okay, so despite the name, confusingly named, but it's actually a model for classification, so linear model for classification. So as always, do the quiz before the lecture, ask the questions on Piazza, and so if you ask them with enough time, we can try and prepare some material for it to go through them. And then you've got your lab session this week. So you've got lab session on decision trees and linear regression. So then the good news for you, I guess, is that at this point, we've actually got all the material you need for the coursework. So your coursework is due in over a week, but actually you've gone through everything at this point. So you've gone through your decision trees, linear regression, and so on. So logistic regression is not required for the actual lab, for the actual assignment. Okay, so I think people are already aware that the coursework 1 is due on October the 20th, 4 p.m. So take note, there's no extensions. and it's worth 20% of your final grade. Okay, so if anyone, I'd advise you to kind of get started now if you haven't already, just because there's a bit of setup involved in like downloading the LaTeX template and building it for the first time. So you certainly don't want to be kind of trying to do that very last minute in case you get stuck or you're a bit unfamiliar with it. But the thing to note is, again, you've got two options for building your PDF. So you're going to upload a PDF, but you have the option to do this on Dice via the command line, or you can do this on Overleaf, so online editor. Okay, coursework 1 is due next week. And so the important thing, like I said before, do the correct coursework corresponding to your the course that you're on. So level 11 has one extra question. Don't discuss on Piazza in the labs, tutorials, or class sessions, for example. And I see people are starting to ask some private questions on Piazza. So really, Piazza is not a place for us to provide hints for the assignment. If something truly is ambiguous, we'll take note and we'll make an announcement. So I'll make an announcement about something in the next slide. But really, don't expect to be able to get any kind of pointers or hints from us. So it really is just for cases where something is not actually clear, not if you're not sure if you're doing the right thing. Yeah, and like I said before, use the correct package versions is very important. Okay, so just a couple of notes on the coursework. These were some of the things I think people were slightly unsure about. And so I'll go through them here, and then I'll also, by the end of the day, I'll either put this on Learn and GitHub, but I'll also email this to people so they're aware of it. Okay, so someone asked, for example, a question, which hyperparameter should I use? So the assumption should be, if for a given question, because as we know, sklearn, scikit-learn has many different hyperparameters, choices for different things. So if it's not specified explicitly that you use a particular parameter, you should just use the default. And that's why it's very important to use the same version of sklearn that we specify, because sometimes those things can change, or there can be minor differences. So again, like I say, if it's not specified, it's implied that you use the default settings for something. Okay. Yeah. Okay. And again, someone else asked, can I use a NumPy function for X, Y, or Z? Unless you're requested to actually explicitly implement something yourself, okay, which it does say it in one or two places in the coursework, you can use the built-in functions in sklearn or NumPy. Okay, so there's only, I think, one or two places where you might be expected to actually report some code. One of the things that maybe is actually slightly ambiguous is question 3b. So this is the one on decision trees. It asks you to plot the mean of the data. It doesn't actually specify which split of the data you should use. And so it's reasonable to assume that you should do the train. The very least, like in all cases, whatever you plot, you should just make it clear what that is. So if you are plotting the train, you write that this is the train data. Okay, so that's maybe one of the ones that's probably the most ambiguous. So just take note of that. Question 3b, should plot the train data. And again, someone else asked, some of these data sets, we don't actually explicitly provide a validation set. Some of them don't have a test set. Again, don't do anything more than what you're asked to do. So don't explicitly split the data up into train and validation, for example, unless you're asked to do so. Okay, so there's no trick questions in here asking you to do things like that, and we don't expect you to end up with a different slice of the data than we're expecting you to work with. Okay, and so submission. So like I said previously, your LaTeX template is going to build a PDF. From that PDF, that's the PDF that you're going to submit. That's the only thing that you're going to submit. So there's no Jupyter notebooks, there's no extra code documents or anything like that that you're expected to upload as well. The places where you are expected to provide some code, it's not expected that this is pages of code. This should only be on the order of a few lines, just necessary functions that you are required to submit. And we'll provide more detail during the week, but basically we'll be using an online system called GradeScope. Okay, but like I said, there'll be more information provided for how that works. But basically, what this will do is you'll go to this GradeScope website, you'll upload your particular assignment, you'll tag each of the pages with the corresponding questions, and it'll get graded by us via that mechanism. Yeah, I mean, so Lars makes a good point as well. If we go back here, it's pretty bad to plot your test data, no? So it would be, let me write it here, it's bad to plot test because you really shouldn't be looking at the test data. Because if you're looking at the test data, obviously there's some kind of leakage. You're finding out something that you wouldn't know, and really all you're doing is you're hurting yourself because you're overfitting potentially to the test data set. So it's a pretty uncontroversial thing to do to plot the train. Certainly not a good idea to plot the test, unless you truly believe that there's something fundamentally wrong or different distribution with your test data. That might be something that you might consider doing without looking at the labels, for example. Okay, so where are we go? How are we doing in terms of schedule? So we're actually we're doing well. We're nearly about halfway through the course. So we're powering through the supervised content. We've looked at some of our simple linear models. We've also some nonlinear models for classification as well. Next week, our next class session, we're going to do logistic regression. And then actually from next week onwards, we're going to switch over. So I won't be doing the class sessions anymore. It'll be Chris Williams doing them. So Chris will take over from the SVMs onwards. So he'll look into some more models for classification, and then he'll start looking into some of the unsupervised learning stuff. Okay, so that is that. Let me have a quick look through the chat here to see if there's any relevant questions. RBFs. Yeah, okay, so I'll try and fit in RBFs next week if there's time in the logistic regression. I didn't actually see any questions on Piazza about it, so I didn't think that there would be a problem, but I will potentially try and look at that next week if I have time. And like I said, I think it does come up again in the SVM lectures. Yeah, okay, I'm taking a note. What else have we got? Someone asked how does GradeScope work? So we'll give detailed and clear instructions for how you should, how that will work. So you don't need to go ahead and engage with GradeScope yet, and wait till basically we tell you what to do, and we'll be doing that very shortly. So I'm just going back through. There was a question actually. Okay. Yeah, okay, someone said there's this question that the loss can be interpreted probabilistically, that and it's equivalent to maximizing the likelihood. Yeah, I didn't get to go through that today, but I would suggest take a look at that yourself, think about it again, and that's actually kind of an interesting question to look at in the context of linear regression. But you can show basically that these two things are equivalent. So minimizing the loss is equivalent to maximizing the likelihood of our model where we assume this Gaussian noise. So like I said, I think I said it already, you'll get instructions for how to submit on GradeScope, so no need to worry about that just yet. We'll tell you quite soon. And you should not explicitly split data unless you're told to do that. That's correct. Okay, so we're at time. I will stop there. Like I said, next week, logistic regression. If there is some time, I'll try and do. I'll try and talk about RBS. But maybe in the meantime, I know many people might do it, but if one person could consolidate a question on Piazza, and maybe others can reply to it instead of having multiple people write the same question about RBS, write the question about the thing that's not clear, and then we'll be able to use that as a starting point. Someone's asking a question, how many significant figures? Again, this is bordering on questions about the assignment, which is not something that I told you that you're allowed to. So you really have to take care of the rules and not actually discuss the assignment. So you should just use common sense for some of these questions. Yeah, and then the last question. So someone says, can we add a picture of code? It actually says in the instructions that you're allowed to do that. Okay, so just read through the instructions and you can put it in there. So that's absolutely fine. You don't have to write it out in LaTeX. What's someone asking partial marks? It wouldn't give. What, I'm not sure what the question means. So what is the question, George? Maybe you can quickly say it before we go. Will there be partial marks? Yeah, so it's not all or nothing for each of the questions. Basically, there are you'll be dot marks if you miss out on certain things. So yeah, it's not all or nothing if that's the question. Great. Okay.